Good morning, students. Today's lecture is basically on the boundary layer theory and its applications. The in the first lecture was on introduction of the boundary layer. Now today we will discuss that as in lecture two. Today in lecture two we will discuss the boundary layer equations and its formulations, how the boundary layer equations are formed. Now the objective for today's class are two learning objectives. That is, what is the scales in boundary layer flow and the boundary layer equations. Now, these equations or the scales were introduced by Prandtl, and the boundary layer equations were also introduced by Prandtl, and they are called as Prandtl's boundary layer equations. So let us quickly review the different terminologies which we have already studied. Now, the first part, first is this that there is a flat plate over here. I have shown a flat plate on which there is a uniform stream of flow. Now, this uniform stream may be a function of x, that is the streamwise direction. X is the streamwise direction and y is the wall normal direction. So u infinity may be function of x and may not be a function of x. So if it is, if, so the first thing which comes into play is what is the boundary layer, thick boundary layer. So the boundary layer is shown by this light blue line, which is over here, and this demarcates the viscosity dominant region and the no viscosity region. Now the no viscosity region behaves as the potential flow region, while the viscous boundary layer behaves as the viscosity dominated region. Now this length, which is at the interface, which is at the position where y is equal to 0.99 times of the free stream velocity, is known as the boundary layer thickness. So the velocity at any y is equal to 0 is 0, and at the boundary layer thickness, that is y is equal to delta, which delta is equal to 0.99 times of u infinity. Now this delta x basically changes its length with the x direction. Now, what is the procedure to obtain these equation is that we take the Navier-Stokes equation, which is valid for the entire flow. Then we we non-dimensionalize this boundary layer equation by choosing the appropriate scales. The choice of a scale is the key in the whole exercise, and then we try to assimilate or understand or try to calculate or try to guess or guess the order or of magnitude. That means how the different terms are larger or smaller in comparison to each other. And so by retaining the higher order terms, we get the boundary layer equation. Now, uh, so I think those slides were paused. Okay. Now, in the last lecture, or sorry, the module two, you must have been introduced by the non-dimensionalization and why it has been done. So let us use that knowledge. So u is equal to us. U will be scaled by the velocity us. V will be scaled by the velocity vs. X will be scaled by the length scale. So s suffix x basically denotes the scaling values, scales, and you can choose anything for the scale. Like I can, for scaling u velocity and for scaling v velocity, I could have used us as the scale. So there is no need in our last in the exact solutions or the non-dimensionalization which you have already studied. We normally used scales for one scale for the velocity. That means, so for every direction of the velocity, we have not used till then these scales, different scales. Neither we have used different scales for the direction also. So, so the length scale for the x direction is a length, but here we are using for the y scale, instead of using L, we are using delta L. Similarly, we are doing the same with v velocity. We are not using the same scale for the vs velocity for the v velocity as the us. For x direction, that is the streamwise direction, we use us is equal to u infinity, which is the scale of velocity. Us is the scale of velocity. U infinity is the velocity which is outside the boundary layer. So the non-dimensional term u star. So now you can see the star which is at the above dictates or shows all the terms which are u star, v star, x star, y star, t star. These are all our non-dimensional terms. So in our last lecture, we have shown that will be equal to u by u infinity, v star will be equal to v by v infinity, vs, x star will be equal to x by xl, y star will be y by delta L. Now, we do not know what will be the velocity. Like us, we know that the streamwise velocity outside the boundary layer is the us velocity, is the u infinity, which we already know. Now, but Prandtl decided to use a different velocity for the vertical velocity. He said that the value or the magnitude of the vertical velocity present in a streamwise, in this kind of a flow, in the boundary layer flow, is very small. So, and this velocity is important, but this velocity is important because it decides about the what is the transfer of momentum across the streamlines. That means in the y direction, the streamlines. So the momentum from one surface to the other surface is basically carried by the v velocity. So the scale of v velocity is very important. But right now we will just we do not know what the value will be. So we will just put a question mark and decide what is try to calculate the Vs scale from anything which we have known. Okay. Now, since u is scaled by u infinity, we will say that because both are the similar terms, so they will be this we call as the order 1 term. Similarly, v star, which is v by vs, so this is also order 1 term. X by L is also order 1. Similarly, y by delta L is also uh, y by delta L is also of the order of 1. Now, now if I take now there is a for time also, we can use this ls upon us, which is L upon u infinity, which gives t u infinity by L, which is again of the order of 1. Now, the governing equation for any incompressible homogeneous viscous fluid these are the governing equation in x direction in Cartesian coordinate system for two-dimensional flow. So as you see that the continuity equation is del u by del x plus del v by del y. X momentum is this, y momentum is this. So these are called the Navier-Stokes equation. So I will go on directly to the non-dimensionalization of these equations, which are this. So this is slightly a full slide. So let us use this slide. So the continuity equation. So in the left side, I have written the dimensional form of this equation. On the right side, I have tried to write down the non-dimensional form of this equation. And this is just to use by using the scales which we have already studied, shown. I have already discussed with you. So now del u by del x or del v by del y, you multiply u star. So since u by u star is equal to u by u infinity is equal to u star. So instead of the u, we substitute u star into u infinity. Now, u infinity a constant quantity, it comes out of the boundary layer. It comes out of the partial derivative. So it becomes u infinity, and in the denominator this is del u star by del x star. So now x is substituted by x star multiplied by L. So this becomes u infinity by L. Now I do not know the scale of right now Vs. So V star is Vs upon delta L. So the choice of Vs, I have just I have not put the value of V star Vs. I've just retained the Vs over here. Now similarly, I have done this for all of these equations. So you can have a look at these equations and try to use a copy and pen and try to do it yourself. So now, since I do not know the V velocity scale, I am going to use this continuity equation which I have already discussed over here. Now u infinity by L, so this is the continuity, the non-dimensional form of the continuity equation I have written. Then if you will see directly below, now since these are the two terms which needs to be make it equal to 0. So that means del u by del x, or as a whole term, must be of the order of 1. And similarly del v over del y must be of the order of 1. So that means these two terms are basically of the similar order, and this can only be possible if del u star by del x star is also of the order of 1 and del v star by del y star is also of the order of 1. And the Vs over delta L, that is the coefficient of the del v star by del y star, must be equal to u infinity by L. So this gives you the Vs as u infinity by L into delta L. Now this is a very important thing to understand. So that means this is the value which I am going to substitute back into the above x momentum and y momentum non-dimensional forms. Now, if I try to ascertain what is the size of the or the order of this of Vs, then you can see that delta L upon L is sorry u infinity over L are basically of the order of 1. So which implies that Vs will always be of the order of delta L. Now if I use the delta L over k is equals to R e raised to the power L, then I can also say that Vs will be of the order of u infinity into REL raised to the power of minus half. Now this information, which is the first information, which is Vs is equals to u infinity by L into delta L, I am going to use in the next slide. Now in the next slide, I have only the continuity which I have evolved in the non-dimensional form, and the x momentum I have written. Now in the x momentum, the y x the you can see the working out over here. I have substituted as u infinity delta by L instead of Vs, and then I have tried to try to what you can call simplify it, and you can see the above equation. The RHS has apart from the important part is this. So if I want to have a dynamic scale over here, so P dynamic will be equal to P star dynamic will be equal to P dynamic divided by rho naught into u infinity square. So L and L cancels out. So to become this term to be non-dimensional, the scale for P star, it will be equal to uh, rho naught into u infinity square or us square. So now finally, if you will see that now this becomes equal to del u by del t star u star del u star by del x plus the pressure term plus the viscous term has this 1 over REL multiplied by del 2 u by del x square, that is the x direction derivative of the viscous term, and delta L over L square, which is the y direction derivative over the multiplied by the y direction derivative of the viscous term, non-dimensional form. Now let me use the y momentum equation. Now I have done the simple same thing over here again. Use substituted y star, substituted Vs over here, and you can see the maths over here. Similar thing have been done. So you can see that there is a lot of other things also had come into the last equation, which is over here. Now if I Now comes the very important part, which is the order of magnitude analysis. Now, as you see that, since U star and T star are the order of 1, so the gradient will be also of the order of 1, which I have shown you over here. Uh, now, if I now these are all we will apply as when REL is much greater than 1. So 1 over REL must be much less than 1. So this we will use in this. Now U star is also of the order of 1, and del U star by del X star, which we have already seen, is also of the order of 1. So now this whole term is also of the order of 1. So LHS, whole of the LHS, is basically of the order of 1. Now, if you will see on the right RHS, again, these are all star quantities. Nothing is multiplied or divided with this. So these are all of the order of 1. Now here, this is the important stuff, which is going to give you a very easy equations. Now, 1 over REL is multiplied with del U2 by del UX square. Now, since del 1 over REL is basically a ratio of 1 over of the Reynolds number, inverse of the Reynolds number, so the order of this term will be obviously of the order of 1 over REL. And since the derivative del 2U star by del X square has only star der values, so they will again be the of the order of 1. Now, 1 over REL again is the of the order of 1 over REL, but delta L by L square, L square by delta L, sorry, delta L square from this, if you will remember this, which I have discussed over here, if I square the delta L over L, delta over L square, so this the order of this becomes inversely proportional to Reynolds number. So if L over delta L square, then that means this becomes REL. So this term, the middle term is of the order of REL, and again del 2 U over star y star over del y square is of the order of 1. So combinedly, the second term of this of the second term of the viscous term is of the order of 1, but the first term of the viscous term is of the order of 1 over REL. Now all the terms which are the rest of the LHS is of the order of 1. The P dynamic is of the order of 1, but the first term of the is of the order of 1. Now, if I want to see the what is the value of REL, now you already know that the REL must be greater, much greater than 1. So that means 1 over REL will be much less than 1. So this term automatically becomes much smaller to 1. So that means if I retain all the terms of the order of 1, then I have to drop this part from the boundary layer equations. So which implies that the boundary equations, the new boundary layer equations, becomes this, the term which is at the right, the equation which is at the rightmost part of the slide. Now if I, so and this is the x momentum equation, mind you that. Now again I am using the y momentum form of the Navier-Stokes equation, which is given in the two slides before. Now again you see that delta L over L square is there, which is of the order of 1 over REL. The rest term or rest of the terms in the LHS are of the order of 1 because they only have the derivatives of the star derivatives over there. Multiplying by the delta L over REL is there. So the LHS, so whole of the left hand side becomes of the order of 1 over REL. Now del P over dP over d dynamic is of the order of 1. Now you can see that the first term that is delta 1 over REL, while the other term is first term of the viscous term is 1 over REL, and the second order term is of the order of delta L over L, again is also again of the order of 1 over REL. So this is 1 over REL square. Now the third term is of again of the order of 1. So the combinedly this term is of the order of 1 over REL square. The second term of the viscous term, the second term of the viscous viscous part is 1 over REL, while the derivative is of the order of 1. So this term whole combinedly becomes 1 over REL term. So that means either there are the LHS whole is of the order of 1 over REL and or lower terms. So if I take T del P by del the pressure gradient on the x-axis on the left hand side and put all of the terms on the right hand side. So either the right hand side are the terms on the right hand side are either of the 1 over REL or below that. So therefore I can safely say that. So we can conclude that 1 over RE naught or pressure dynamic, the pressure gradient of the in the wall normal direction, that is the pressure, the y direction, becomes 0. So what this helps is, let us first summarize and then I will try to explain what happens when the y direction derivative becomes 0. So if we have boundary layer equations. Now for the first thing and the foremost thing is this: the boundary layer equations are only valid for flows which are much greater than 1. So uh, so the continuity equation becomes is the familiar del u by del x and del u by del y. There is no change in the continuity equation. The x momentum equation, there is a change. You can see that there is no, the viscous term doesn't have del 2 u by del x square. And the y momentum, the most change is the y momentum, where you can safely say that the del p dynamic over del y becomes equal to 0. Now, what is the implication of this pressure gradient becoming y? So if you are outside the boundary layer, that means before this, when u is equal to u infinity, this p dynamic outside the boundary layer, since p dynamic it doesn't have a variation in the y direction, the outside boundary layer pressure will be same inside the boundary layer. So whatever is the pressure is outside the boundary layer will be same as inside the boundary layer. Now, if I go to the next slide, which is over here, so the dynamic pressure inside the boundary layer. Now del P by dynamic by del y is equal to 0. That is what I have explained over here. The dynamic pressure inside the boundary layer, it's, at any station x is same as outside the boundary layer or the inviscid flow region. Now this outside boundary layer pressure has a very significance. Since outside boundary layer pressure is equal to the inside boundary layer pressure, and the outside the boundary layer the flow is inviscid. So outer inviscid flow pressure basically dictates what is the pressure inside the boundary layer at the wall. That is the meaning of this. Secondly, what it helps is, instead of calculating the pressure gradient del P over del Y and del P over del Y, we can safely use the del P over del X. We can safely use the Euler side of momentum equation. And since Euler side of the momentum equation, there's no gradient of y velocity in the del u infinity. So outside the boundary layer, del u infinity by del y is 0. So this becomes the form, and I can substitute in the momentum equation this the x momentum equation in the x direction boundary layer equation, this expression which is at the bottom of del u to u infinity by using the Euler's equation, and I get the basic full boundary layer equations, which is this. Now which is the continuity equation is del u by del x plus del v over del y. X momentum is this which is over here, and now this expression, the term which is in the bracket, is basically the term which needs to be determined from the inviscid solution. Now if you already have a form of u infinity, that means you do not have to calculate the pressure gradient in the x direction. You just need to calculate the u infinity, this part and you know the x part. Now, and the y momentum, which is again I have written del p over del y equal to 0. Now the boundary conditions are very very easy. Since there is a no slip at y is equal to 0, u and v velocities are both 0. As you go to the becomes infinity, u becomes equal to u infinity and v becomes equal to v infinity. But v infinity is not a significant thing. U just becomes equal to the u infinity. Now, what from here you can see that for any station x, that is for any x station x, uh, there is a variation of y and t. So that means for any x0, there will be only the variation will be in the y and t direction. This gives you the hint of self similarity also, which we will discuss later down the stream. And the initial conditions are basically specified. Now, I can also use the velocity the continuity equation to express the v velocity, which is like this. I can integrate partially with respect to y, and I get this form. So this will gives you the v velocity is just equal to from just equal to 0 to 1. So instead of using either the continuity equation or continuity coefficient differential form, or we can use the vertical velocity, the integral form of the velocity. So then therefore now the final boundary layer equations on in a Cartesian coordinate for a flat surface is given like this. Whether it is accelerated or deaccelerated, you have these are the boundary conditions. Y is equal to 0, u and v is 0, and y is equal to infinity, u is equal to u infinity. So now these are very important, and all the higher order derivatives of y are 0 for all x. Now this is very important. This is not only at y is equal to 0. This is at all x. The higher order derivatives are 0 at y is equal to 0. Now, so if the flow is steady, then we have these are the boundary conditions. You just drop the unsteady part and you get this boundary. This is the zero pressure gradient. So this is the boundary layer equations. If you have a zero pressure gradient, then du infinity by dx is also 0. So you have u del u by del x, v del v by del y, and plus mu naught del 2u over del y square. So this finishes our talk on the boundary layer equations, and I will in our next class discuss boundary layer separation and other things. Thank you.